right, so we're starting at Kirkwood. All right, let's get an idea of the directions we're going here. I'm traveling west. So I'm heading out this direction. Now, one of the things you need to ask yourself as you're setting up these problems is that direction I'm going, is that distance I'm going, is that a distance that's changing? If it is, you need to assign a variable to it. We'll let x represent that distance. Now, I know eventually in this problem we have an exact mileage that I've gone, but we know over time that distance is changing, so we assign a variable. Okay, we've got the basic algebra class. They're traveling north, so they're going this way. We know that distance is changing over time, and eventually we'll be concerned about a specific distance at some point in time. But for the time being, I'll label that y. Now, in the end here, we're asking about how the distance is changing between the two of us as we head our separate directions. So there's this distance right here. And as this distance x increases, this distance y increases, we know this distance here is going to change, so maybe I'll make that distance z. And what I'm trying to do at this point is I'm trying to come up with some kind of equation that brings together these distances somehow. So I mentioned a little while ago how a lot of these problems, there's usually a way to connect to a triangle somehow, some triangular relationship. Since we have a right triangle here, we could use the Pythagorean theorem to link x, y, and z. And the way we do that, x squared plus y squared would have to equal z squared. That'd be simple enough. Now, once you set up an equation that brings together all of these variables, what you want to do is you want to take the derivative of that equation with respect to time. So if x squared plus y squared equals z squared, if I take the derivative of x squared, I get 2x. If I do so with respect to time, I'm taking the derivative of x with respect to time, I apply that dx dt. Similar idea for y squared. We add on to y the derivative of y squared. We're taking the derivative of y with respect to time, so I apply dy dt. That equals 2z dz dt if I follow the same pattern. All right, now I got to think about what all these variable expressions mean. The x, the y, the z. These represent distances. And ultimately, there are some distances here to play with, right? Like, I'm concerned about what's happening at the moment in time where I'm 30 miles away from the high school, right? So when x is 30. I'm also concerned about the moment in time when they're 40 miles away from the high school. So when y is 40. I could plug in 30 for x, I could plug in 40 for y, right? That could be information I could insert at this point. But these other values, all these derivative notations, well, that's how those distances are changing over time. So those are my velocities, my speeds. You know, the dx dt, since that's connected to how x is changing over time, that goes with my speed. The dy dt, that's the change in y over time. That goes with their speed. So we know my speed is what? My speed is 40. That would be dx dt. And we know their speed is 80. That'd be dy dt. So we could start plugging all this information in. If I plug it in, we've got 2 times x. X is the distance that I am away from the high school. What was that distance again? It was 30, okay. dx dt is the speed that's associated with me. So my speed was 40 miles per hour. We add on 2 times y. Let's see, y was the distance they were at when I was 30 miles away. They were 40. And then dy dt is their speed they're traveling. They're going 80. And that equals over here 2 times, okay, do I know z or dz dt? At some point here, we need to get down to one variable to solve for and hope that that one variable expression is what we're looking for. Do I know either of those? If not, could I figure out either of those pretty easily? Yeah, I could figure out what z is pretty easily. If I know what x and y are going to be, I know x is 30, I know y is 40. Let's go back and let's use this equation. Plug in, you got 30 squared. Plug in, you got 40 squared. That equals z squared, right? Go through, solve for z. Now, if you're on top of your game here with your Pythagorean triples, you already know what z is going to be. What's z going to be? 50. So when I'm 30 miles away, they're 40 miles away. We know the distance between us is 50 miles. So we can insert now 50 in over here. Leaving dz dt, which is the rate at which z is changing. That means that's the speed at which it's changing between the two of us as we travel away, right? And if you look at the question here, that's what we're trying to find. We're trying to find dz dt. So the good news is we have enough information inserted in for all the other variable expressions that we can simply solve for dz dt here. The easiest way to do that, I know 2 times 50 is 100, so I'm just going to divide 100 over here. That gets dz dt by itself. If I do this calculation now, whatever I get back will be that speed at which it's changing between the basic algebra class and myself. It'll be in miles per hour, right? Anybody know what that value is going to be? I came up with 88. You can check me on that, but I believe it's 88 miles per hour. Okay, so we have to use that volume of the sphere formula to help us answer this question. And unlike the last problem where we had to set up an equation for us to use, since we already know what the formula is going to be, we can go ahead and take the derivative off of this formula and then start plugging in what we need. So if I take the derivative of this formula, starting with the v, if I take the derivative of v, I'm just going to get 1 back, right? Just going to get 1 back, and I will have taken the derivative of v, so I'll write dv dt. So derivative of v is 1 dv dt. That equals, okay, we got 4 pi r cubed on the other side. The only variable in there is the r. So we're going to take the derivative of that 4 pi r cubed with respect to r. If we're doing that, we'll have a dr dt here at the end. So the only question is, what's the derivative of 4 pi r cubed? Well, bring down the 3, right? Bring down the 3, multiply to the 4 pi, you get 12 pi r squared. Oh, it's 4/3, sorry. If you bring down the 3, it's 4 pi r squared. Okay? So this one's a little nicer because, hey, you got a set formula. You just take the derivative with respect to time. Now, plugging in what we need. Well, let's see here. Variable expressions. We've got an r. we need a radius to plug in. We've got a dV dt, a dr dt. So those are my rates that I'm playing with here. I've got to go back and look at this information and see if there are any rates to play with that I could plug in. So let's go back and let's look at the numbers that are given. The numbers that are given on this one. We do have a rate of 100 cubic meters per second. Now I'm letting the air out of the balloon at that rate. Is that going to be pertaining to the volume of the balloon or to the radius? Okay, it's going to go with the volume. And since we're letting it out, it's actually decreasing, right? So we'll let dV dt be a negative 100. That's going to equal 4 times pi. Okay, do I know what r is? Do I know my radius? Yeah, I do, because it says the diameter of the balloon is 200 meters. That means the radius is going to be 100. And those are the only values that were given. There's no other values I can find except for dr dt at this point, which I need to solve for. If I go back and consider the question that's being asked, how fast is the radius of the balloon decreasing? Well, that's going to be connected to that dr dt, right? So solving for dr dt, basically you're going to take this negative 100, you're going to divide by this product of 4 pi times 100 squared. Right? This is all multiplied to dr dt, so just divide that over. Now, when you do that calculation, let's see here, a couple ways we could express this answer. One, if we leave it in the fraction form, it would be negative 1 over 400 pi. I mean, that'd be one way to express it. In terms of the application, doesn't make a lot of sense. So if you wanted to go through and give me the decimal on this one would be negative 0.0008. That would be the rate at which that radius is changing. As far as a unit of measurement is concerned, let's see what we got here. For volume, it was cubic meters per second, right? So this would be meters per second.